Hi and welcome back. This is video 2 of 2 on Chapter 14. Now Chapter 14 introduces us to the concepts of mutual inductance and self-inductance. It also introduces us to the idea of an inductor as a component within a circuit. So what I'd like to do now is to take a look at an inductor, we'll say this one right here, that has current flowing through it. Okay? And then what I want to do is to allow this inductor to just get rid of the energy that it has in it. We're going to shut off whatever's driving the current going around the circuit, which means that as this inductor loses this magnetic field, it'll have a changing flux going through it that will generate an EMF that will take the energy that's trapped within it and use that energy to drive current eventually down to zero. So, that said, this thing is losing energy over time, which means that we can talk about the energy it's losing with respect to power. Now, power is equal to current times voltage, or in this case, current times the EMF, since it's the changing flux that's going to be driving this current back around the circuit. Now, that said, we know in this case it's the energy that's stored within this inductor that would be driving the current around as the magnetic field within it dies off. So what you have is a changing potential energy over time. Now we also know for inductance the relationship between the generated EMF, the number of turns within our inductor, and the changing magnetic flux. It's this right here. And let's not forget that the negative sign just reminds us to not forget about Lenz's law. So if I take this and I put this in here, what I have is the following. du dt is equal to I times N times the change in the magnetic flux over time. Now I'm going to multiply both sides by dt to get rid of the time dependence for right now. On the left-hand side we have a du, and on the right-hand side we have N times I times the changing magnetic flux. And now let's talk about this. Because we know magnetic flux is the integral of B dot N hat ds. It's a surface integral. Now, our solenoid here, which is going to be just like the coils and the solenoids that we've talked about in the past, has fixed physical dimensions, which means that ds itself is a constant. B is a constant over area. Now, it's not a constant over time. So I can turn this integral into just B times the area A. Now, we're talking about a solenoid, and we know the relationship between the magnetic field and the current that passes through a solenoid. It's mu naught times little n times I. Now, little n, if you remember, is the number of turns per unit length, and I'm using cursive L here to avoid confusion with self-inductance. So we also know that we can write big N as little n times L, just rearranging this. So if I were to take and put this in here into our flux, and think about what's changing over here as this thing dies off. Well, mu naught's a constant. N is a physical part, A is a physical part, and what's changing over here is the current. So I'm going to plug this right here into this. And I'd also like to point out the fact that capital N, in terms of characteristics of the coil, is just little n times L. We have a mu naught N times A times di. du here on the left-hand side, On the right hand side, I'm going to pull out everything that's not that is a constant. I have mu naught n squared L times A. On the right hand side, after that, I have I times di. Now, you might recognize this as being the inductance L, the self-inductance of a coil, which is exactly what it is. So, this is the same thing as L times I di. Now let's integrate both sides. So on the left-hand side, we have du. Now we're starting with our coil having the maximum amount of current passing through it, and then we're letting that current die off to zero, which means our coil has plenty of energy trapped within it initially, and then as it dies off to zero, we expect that energy to go to zero. On the right-hand side, my L is a constant. I have I di. We're starting our current off at a maximum I, and then it drops off to zero. Now, as we integrate both sides, on the left-hand side, I'll have a U evaluated from U naught to 0. On the right-hand side, I have an L with a 1/2 out front and an I squared. I need to evaluate this from I to 0. Now, when I evaluate the left-hand side, this becomes minus U naught. When I evaluate the right-hand side, it becomes minus 1/2 Li squared, which means that the potential energy that I start off with, which we're just going to call U, is 1/2 L times I squared. So this is one way that you can think of the potential energy, and it should look very familiar to us. If you look at, say, the potential energy within a capacitor, it looks like 1/2 CV squared. So the potential energy inside a capacitor is 1/2 CV squared. The potential energy within an inductor is 1/2 Li squared. So a lot of similarity here. Now, not only that, I can take this right here and massage it to see exactly where that energy is hiding. So my potential energy here is 1/2 L times I squared. Now, for a solenoid, for what we're dealing with right now, my L is mu naught n squared times the length times the area, or the cross-sectional area of our coil. Now, I, we can get from this right here. I is B over mu naught times N. So this would be B over mu naught times N, but it's squared since this is I squared. Now, if you look at this and this, there are actually some cancellations going on. I have an n squared here, I have an n here, but it's squared. That's going to go away entirely. Now, I have a mu naught here, but I have two mu naughts in the bottom, so I'm going to lose one of those. And what this says is that the potential energy that I have, U, is equal to 1 over 2 mu naught times L times A times B squared. Now, what I'd like to do is to turn this into an energy density and talk about the total amount of energy that's trapped within the volume of the solenoid. And if you look over here, this is the length of our solenoid, this is the cross-sectional area, this is V, this is the volume. This is, in the previous video we wrote it like that. So potential energy over V is what we know as energy density, lowercase u. It's 1 over 2 mu naught times the magnetic field squared. So what this says is that the energy is trapped within the magnetic field. That's where it's hiding. And if you go back and you look at our discussion about capacitors, the capacitance of a capacitor stores the energy between the plates in the electric field. So let's do an example. In this problem, what I'd like to know is how much energy is stored in a solenoid with an inductance of 2 times 10 to the minus 4th henries that has 5 amperes of current passing through it. Now it's cylindrical, it's 0.75 centimeters in radius, and it's 5 centimeters long. And I'd like to know what the magnetic field is inside of it. So what we've been given here is the self-inductance. We have the current. We know how long it is. It's 5.0 centimeters or 0.050 meters. And we have its radius, which is 0.75 centimeters or 0.0075 meters. And what we'd like to find are two things. We'd like to find, excuse me, the energy inside, U, and we'd also like to find B. Okay. Now the energy is pretty easy. We know just from the previous work that we did that inside a coil of inductance L, the energy is this right here. So on that note, that would be 1/2 times 2 times 10 to the minus 4th henries times 5.0 amps squared. And if you put that into your calculator, let's see what we'll get here. So 1/2 times 2 times 10 to the minus 4th times 5 squared. I get about 2.5 times 10 to the minus 3rd joules. Okay, so that answers that part. The next question is, what's the magnetic field on the inside? And the way to get the magnetic field would be to go down here and take a look at the relationship between energy and energy density right here. So here we know the energy inside a solenoid is just 1/2 mu naught times the length times the area times b squared, and we just found out U. So from this we should be able to find B pretty easily. So U is 1/2 mu naught L times A times B squared. Now excuse me, B in turn would be 2 mu naught times the energy divided by L times A square root of. Or if you put in the fact that the area, since it's a cylinder, the cross-sectional area of this thing is just that of a circle, that would be 2 mu naught times U over pi times r squared times L, the square root of. So that's what our magnetic field is going to be. So if we plug some numbers in here, 2 times mu naught is 4 pi times 10 to the minus 7th Tesla meters per ampere. The energy we just found out to be 2.5 times 10 to the minus 3rd joules. In the denominator, we have pi times 0.0075 meters squared. That's our radius. And then we have our length, which is 0.050 meters. And we have to square root all of this. So let's see here. You take that, you multiply it by 2, multiply it by 4 pi times 10 to the minus 7th. Then divide by, again, you could just divide the pi's out if you want, but I'm not, times 0.0075 squared times 0.05. And then I'm going to take the square root of this. And so the magnetic field here is going to be about 2.7 times 10 to the minus 2nd Tesla. So there you go. Now, so not so bad. The next thing I'd like to do is to talk about what happens when you start to put these sorts of things in circuits. Um, we've talked about a number of components in circuits so far. Specifically resistors and capacitors. This makes a third component. Beyond this, typically what you start to get into are what are called solid state devices, which, if you were to go off and do a degree in electricity and electronics or electrical engineering or something, you would learn about. That said, what I'd like to do is to imagine a situation where you have a circuit that's just a resistor and inductor in line with each other. Now, this circuit's being powered by EMF from the outside. So let's pretend that, perhaps you have a changing magnetic field across the area of our circuit, and as a consequence, that's inducing an EMF. Now, some percentage of that EMF is going to be dumped across the resistor, because the EMF is just voltage, and some percentage is going to be, dumped across our inductor. Now, that said, if you were to sort of walk around the circuit and think about where that EMF would be, well, some of it's going to go across the resistor, and some of it's going to go across our inductor, like that. We know the relationship between voltage, current, and resistance for resistors. And we also know the relationship between voltage, self-inductance, and current, which looks like this. So this EMF is being dumped in here, and let me just qualify this by putting an L there to show that it's the same thing as that. So our EMF is being, like I said, induced due to some sort of external thing in this particular case. And so what you have here is I times R plus L di dt. And yes, I know there would be a minus sign here, but again, the minus sign is just a reminder to not forget about Lenz's law. So, so what we need to do, or at least what our goal here is to do, is to find the current. Because we know, well, once you find the current, you can find things like voltages and, go from there if you need to find any other sort of stuff in the circuit. So the way I propose doing that is to take and move my my I times R over here to the left-hand side and switch sides. So on the left-hand side, I would have an L di dt. And on the right-hand side, I'm going to have this induced EMF minus, I times R. Now, what I'm going to do is to move the dt over here to the right-hand side, move this L over here to the right-hand side, and move this to the left-hand side. And when I do that, I have a di over my EMF minus I times R on the left-hand side. And on the right-hand side, I'm going to have a dt over L. Now, so what I'm going to do is we're going to integrate this. This is going to be an indefinite integral. So integrate the left-hand side. You're integrating di over the EMF minus I times R. You integrate the right-hand side. You're integrating 1 over L, since that's the constant. I'm going to pull it out. It's just the integral of dt. Now, this is a very easy integral to do. This is going to be t, and then we'll have a constant because, like I said, this is indefinite, which I'll just call C1 that may or may not be relevant. On the left-hand side, in order to make this integrable, what I'm going to do is to do a substitution. I'm going to call U the EMF minus I times R. And when I take the differential of that, that'll be minus R di, just like that, which means that every time I see a di, I need to put a minus du over R there. So the left side is going to be minus 1 over R du over u. On the right hand side, I've already done this integration. That's 1 over L times t plus C1. Now, the next thing I'm going to do before I perform the integral here is to go ahead and multiply both sides by minus r. What that's going to do is to get rid of this, and then on the right-hand side, I'll have a minus r over L times t plus, now minus r times C1 is just another constant, so I'm going to call that C2. And that at this point, what I'd like to do is to define what's called a time constant or folding time. This is for this particular type of arrangement. We're going to call it tau, much like we saw way back when we looked at capacitors discharging into resistors. And here, tau is going to equal to L over R. So I'm going to box this so we don't forget what it is. And so, this, again, when you do the integral on the left-hand side, that's just going to be a natural log of u. But on the right-hand side, now we have a minus t over tau sub L. And then we have our constant C2 there. So the next thing we're going to do is to take and raise e to the power of both sides. When you do that, the left-hand side becomes u. The right-hand side becomes e to the minus t over tau sub L plus C2. Now, check this out, right? So this is just exponent math. This is the same thing as e to the minus t over tau sub L times e to the C2. But e to the C2 is just another constant, which we can pull outside and call that C3 in front of our exponential. So on the left-hand side, we have u. Now, let's not forget what u is. U is the EMF minus I times R. So that would be the EMF minus I times R on the left-hand side. On the right-hand side, we have C3 e to the minus t over tau sub L. All right, so we're almost there. What I'm going to do is to move this to the right-hand side, move this to the left-hand side, because we're trying to find the current. When I move that, it becomes positive. This will be the EMF minus, excuse me, e to the minus t over tau sub L. And then we have our constant sitting out in front, C sub 3. Now I'm going to divide both sides by R to get I by itself. I have my EMF divided by R minus, when you take C3 and you divide it by R, you get another constant, which I'll call C4. These are just constants. Tau sub L like that. Now, okay, so here's what we want to do. If you take a look at this, it's pretty clear that as t goes to infinity, okay, as t gets bigger and bigger and bigger and bigger, this decays more and more and more and more. Okay. So at 0, you're just subtracting off whatever this constant is. At infinity, this would be the same thing as dividing 1 over infinity, which is 0, which means that this goes to 0 at infinity. Okay. Now, likewise, when your current I is at 0, at t is equal to 0, what we should see is the maximum current that you can have, which would be like our coil right here just being a wire, because that's all it is just wire loop back onto itself. Okay, so now let's see if we can't figure out what C4 is. And here's the situation that I like to consider. Let's pretend that what's happened here is that we've, at time t is equal to 0, we turn on our varying magnetic field, which induces the EMF in here. So it's going to start off with a current that's equal to 0. So what I would expect would be initially this to be equal to 0. Now, if I plug in 0 here, what that does is to make my e equal to 1, because e to the 0 is equal to 1. So what that would do would be to make the right-hand side of this look like this. So C4 is equal to the EMF divided by R. Okay. So what that allows me to do is to come up with a pretty clear function for my current with respect to time that's going to look like this. 1 minus e to the minus t over tau sub L, noting the fact that tau sub L is my inductance divided by the resistance. So here's the current as a function of time. So at the very beginning, I have no current, and as time goes on, I get more and more and more as more and more and more inductance happens. Now, as the coil builds in strength, as the self-inductance is canceled out more and more, the oppositional current that's created due to the EMF due to its self-inductance, then what should happen is I'm going to reach some current, I max, which would be the same thing as, when t goes to infinity, we'll say. And as you can see here, it's just going to be the EMF divided by R. So, as an example, we have an LR circuit. Our resistor is 1.25 ohms. It's connected in series with a coil that has an inductance of this. How long will it take for the coil to reach 1/2 of its maximum current? Also, what is the maximum current? Okay, so what I'm going to do is to steal this right here. So this is our circuit. Looks like we're missing maybe a little bit of information here. Can we get it from the problem? Let's see here. We have our time constant. No, we're going to need an EMF. That's the outside energy source. So what I'm going to do is to just give us an EMF here. Let's pretend that the EMF is 12 volts. All right. So here, our time constant is just L over R. We're going to need that. Whoops. So let's just sort of write this down to keep track of stuff. Just like I know my current as a function of time is going to look like the EMF over R times 1 minus e to the minus t over tau. So what I've been given here is my EMF is 12 volts. My inductance is 3.5 times 10 to the minus 4th henries. My resistance is 125 ohms. And what I'd like to do is to find the amount of time it takes for the coil to reach 1/2 of its max current. I'll call that T sub 1/2. And also I'd like to find what the max current is. The max current is just going to be given to us by E over R. So let's start there. I max is E over R. E is 12 volts. R is 125 ohms. If I plug this into my calculator, this is going to be 0.096 amps. So there's that right there. Now, the next question is how long is it going to take for this to reach 1/2 of its max current? Well, we have our current as a function of time. So really what we're looking for is time. And what we'd like is for this to equal to I 1/2 we'll call, or 1/2 I max, or 1/2 E over R. So 1/2 E over R equals to E over R times 1 minus E to the minus T over tau sub L. So this is what we're solving. So the E over R is cancel. We have a 1/2 is equal to 1 minus E to the minus T over tau sub L. If I put this over here, I get E to the minus T over tau sub L is equal to 1/2. This should be reminiscent of a problem that we've worked previously dealing with capacitance. And if I take the natural log of both sides and rearrange some stuff, what I get is that T is equal to minus tau sub L times the natural log of 1/2. Now tau sub L, if you remember, is just L over R. So L over R, minus sign out in front, natural log of 1/2. L is 3.5 times 10 to the minus 4th henries. R is 125 ohms. And we have our natural log of 1/2. And when you plug the stuff in here, let's see, 3.5 times 10 to the minus 4th divided by 125, and then multiply that by the natural log of 1/2. You get about 1.9 times 10 to the minus 7th seconds. So it's very quick. Okay? So pretty easy. Okay, so now what I'd like to talk about is a situation where, perhaps you have a battery in the circuit, you close the switch, and what you do is you let charge build up on the capacitor until it reaches its maximum charge. Then what I'm going to do is to open the switch, keeping the charge on the capacitor, and then take the battery out. So we have a fully charged capacitor. We have our inductor here. And there's no obvious source of potential other than what's already inside the circuit as it is. So then what I'm going to do is I'm going to actually close the switch. So let's pretend that we close the switch now. And, were you to look at the situation using sort of a Kirchhoff's loop analysis, typically what you would have here would be that you have your source voltage V minus the voltage across the inductor minus the voltage across the capacitor is equal to 0. But here we just have the voltage across the inductor and the voltage across the capacitor. So what that means is the inductor voltage plus the capacitor voltage add out to 0 like that. So let's talk about what these are. Well, VL is pretty easy. That's just going to be the self-inductance times di dt. VC is going to come from the relationship between capacitance, voltage, and charge. Q is equal to CV, so this would be Q over C. And what's going to happen when I close the switch is that charge is going to move from the negative plate, creating your current, which the conventional direction is from positive and negative, which would be this way. But in reality, we know it's going the other way. But what happens is charge moves from this plate to make everything overall neutral. So you have a current that flows and then dies off over time as the charge on the capacitor goes to 0. So if I take and plug this in for here, we have the following equation. And next, what I'd like to do is to point out the fact that we know a relationship between current and charge. That is, I is equal to dq dt. Okay, so if I plug this into this, I have L, two derivatives of I with respect to time, plus Q over C is equal to 0. Now the next thing I want to do is to divide both sides by L. When I do that, oops, that's not an I, sorry about that. That should be a Q. I'm getting ahead of myself there. So when I divide both sides by L, what I'm going to do is to pull the 1 over LC out in front of the Q here, and that's equal to 0. Now, okay, so generally what we do at this point is we call, okay, so first of all, this equation is a very well-known equation. This is a spring equation, an equation for an oscillator, something that oscillates back and forth. And what's generally done is the constants that sit out in front of the Q that sits by itself, we usually call omega squared. And that's done with some prior knowledge. So omega squared is 1 over LC, which means that I can write this, and let me just box this here real quick. No, I don't want to box it that way. I want to box it with this. So there we go. It's boxed. So what I'm going to do is to rewrite this equation over here as two derivatives of our charge with respect to time plus omega squared Q is equal to 0. This is the equation for harmonic oscillators, what we call it. Now, there are a couple different ways that you can approach solving this. I'm going to introduce you to one of them, which is called the Euler equation. And what the Euler equation does is to link exponentials like this to cosines and sines through the use of the imaginary number I. Now, this is sort of the general solution, or at least one version of the general solution. Usually what's done is you put a plus or minus here, noting the fact it could be either one. And what that does is to put a plus or minus here, at the end of the day. But we're really only interested in the real part of the solution. That is the part that doesn't have an imaginary number. It's the cosine one. But what I would like to do is to show you how if you plug this into here and you do your derivatives, it allows us to figure out the relationship between B and the rest of them. So the general solution that we're going to look at here is going to be our Q as a function of time is going to look something like A times E to the plus or minus BT, IBT rather. So this is our guess. We're going to guess that maybe this solves it. So if I take a derivative of Q with respect to time, A is a constant. Ultimately, we're going to find that based upon some assumptions we're going to make about what's going on here. So A is a constant. Nothing's going on there, really. We have a plus or minus I BT up here. When you take the derivative of this, this is going to come down. And then you have, you have A, E to the plus or minus IBT again. If I take another derivative of Q with respect to time, I'm taking the derivative of this. When I do that, again, the same thing happens. You get a plus or minus IB come down. A plus or minus times a plus or minus works like this. Positive times a positive is a positive. A negative times a negative is a positive, so it's a plus. So you're going to get a positive you have an I times an I. Remember, I is the square root of minus 1. So when you multiply I times I, that's minus 1. So you get a minus b squared times ae to the plus or minus ibt. So generally what's done is you plug these things in to your original equation and then see what in your equation is equal to what constants we have laying around. So that's one of the ways that you're able to eliminate one of the unknowns. So the second derivative of charge with respect to time is minus b squared times ae plus or minus ibt. Plus omega squared times q, and q is just a e to the plus or minus ibt, and that's equal to 0. And what you'll notice here is that the a's cancel. This cancels right here, which means minus b squared plus omega squared is equal to 0. That's the condition that we need to satisfy. And what that really means is that omega is equal to b. So they're the same thing. So at that point, usually what's done is you say, okay, we're only interested in solutions to this thing that give us real stuff, real numbers. And this I that sits out in front of the sign is problematic. It only affects the imaginary world, and we live in the real world, which is this. So we know what B is now. B is omega. So your general solution that you would use here would be the real part of this, which would look something like this. Q of t is equal to A times cosine of omega t. And then sometimes what's added on the inside to give us another potential, we call it a phase. Basically, it's offsetting things in time, potentially, or whatever, would be phi, and phi would be something that you would solve for. We're going to disregard that now. The phase angle really is only relevant, in more complicated situations. So this is what our charge is going to look like. We still have to figure out what A is. A is an unknown. And the way you do that is to take a look at our problem and ask the question, okay, do I know what the charge might be at certain instances in time? And it makes sense to say that initially at time t is equal to 0, the charge on my capacitor is going to be at its maximum, which I'll call Q naught. Okay? So what that means is that when this is equal to 0, okay, and cosine of 0 is 1, that should be true. So that tells us what A is. So here's our solution to this. Our charge as a function of time is going to look like Q naught, excuse me, times cosine of omega times t. And omega is equal to the square root of 1 over, if you look over here, L times C. So it's periodic. So what we expect to happen is this. The charge is going to leave the negative side flowing towards the positive side. And as it continues to do that, because of the presence of the inductor, what that does is to cause the charge to build up and then bounce and then build up and then bounce and then build up and bounce as these sides alternate between positive and negative, negative and positive, and so on like that. So it's periodic. Now from this we can also get the current as a function of time, because I is just dq dt. So if you take the derivative of this with respect to time, the derivative of a cosine is a minus sine. You have to use the chain rule to bring the omega out, which means that this would be Q naught times omega sine omega t, and then you have your minus sign sitting out in front. So right here, this right here is your charge as a function of time. Here's your current as a function of time. And then here is the period that these things oscillate back and forth at. So, so here, what we have is a circuit that has an inductor and a capacitor in it. And the capacitor has been charged. It has an initial charge of 4.2 times 10 to the minus fifth coulombs. Now, the inductor itself has an inductance of 2.5 times 10 to the minus fourth henries. Our capacitor here has a capacitance of 3 times 10 to the minus 6 farads. And what we'd like to do is to find the maximum current and also the period that the circuit's going to oscillate at. Because what's going to happen is charge is going to flow from the negative side to the positive side and switch polarity again, causing this to be negative and this to be positive. And then it's going to flow back, so it oscillates back and forth. Hence the reason, why we got the solution looks the way that we do. So let me borrow this actually, because we'll be using that, to do our problem here. So I'm just going to stick this down here to help us. And so let's write down our givens. We have a charge initially of 4.2 times 10 to the minus fifth coulombs. We have a capacitance of 3 times 10 to the minus 6 farads. We have an inductance of 2.5 times 10 to the minus fourth henries. And what we're trying to find here is the period. We're also trying to find the maximum current. And then we want to plot stuff. Okay. So let's start with the period first, because the maximum current here is going to be given to us when the argument to sine here makes sine equal to 1. When that happens, if you think of a sine wave, you're at a peak or at a trough of your sine. So it's going to be just Q naught times omega. So in order to find I max, we're going to need to find omega. Now, omega is an angular frequency. That's the way we think about it. And this is periodic motion. And if you think about how angular velocity works, if you're going around something at a constant rate, you go through 2 pi radians every period. So here's the relationship between the period and omega. So the period here, t, is going to equal to 2 pi over omega. So all we need to do really is to find omega at this point. So omega is equal to the square root of 1 over LC, which would equal to the square root of 1 over L, which is 2.5 times 10 to the minus fourth henries, and C, which is 3 times 10 to the minus 6 farads. So, if we just find omega here real quick, it's going to be 1 divided by the square root of, let's see this, 2.5 times 10 to the minus fourth, 3 times 10 to the minus 6. I get something like 3.65 times 10 to the fourth radians per second. Now the period is going to be 2 pi over that. So if I take 2 times pi and then divide it by my answer, I get 1.72 times 10 to the minus fourth. So what that means is that the charge is sort of ripped off of this, hits this, and then is ripped off of this and goes back every 1.72 times 10 to the minus fourth second. So that's your period. So that was easy enough. Let's just box that. Next up, we have the maximum current. Well, again, that's going to happen whenever the argument to our sine gives us a 1 or a minus 1. So really what that means is that I max is equal to Q naught times omega, which would be equal to Q naught, which is 4.2 times 10 to the minus fifth coulombs, times omega, and omega was 3.65 times 10 to the fourth radians per second. So if you do that, let's see, times 4.2 times 10 to the minus fifth, I get 1.53 amperes. So that right there would be your max current. Now what about plots? Well, I've already plotted these for us. So what you're looking at here on the left-hand side, this is the charge. And on the right-hand side, you have the current. So let's pretend that your capacitor is charged up with 4.2 times 10 to the minus fifth coulombs worth of charge. When you close the switch and you allow the current to flow, what happens is the charge goes down. It decreases, and as a consequence of it moving from one side to the other side, you have current created. Okay? Now, the current hits its peak right here. The charge at that point is equal to 0 on the capacitor because all the current's moving. So it hits the other side, builds up. At this point right here, which would be this point right here, you can see the current starting to move the other way. So they're out of phase just by a little bit. And that's due to the fact that it takes time for the inductor to build up current as a consequence of the self-inductance. It's constantly trying to oppose the flow of this charge from one side of the plate to the other side. Now, so that said, let's kick things up a notch and talk about what happens when you put all three components in the circuit. We have a capacitor, we have a resistor, and we have an inductor. This is equal to, we call this an LRC circuit. Sometimes it's called an RCL circuit. It's just some combination of three letters generally. Now, so as before, let's pretend that you take and you put a battery in line. And what you do is you let the capacitor charge up fully. We'll say that this right here is the positive side. And then what you do is you open a switch right here, and then you take the battery out. You close the switch, and you let the capacitor discharge. Okay. So at that point, what you have is you have voltage across the capacitor, you have voltage across the resistor, and you have voltage across the inductor. So across the resistor, well, that's just given to us by Ohm's law. Across the inductor, that's L times di dt. Across the capacitor, that's just Q over C. So, just like any Kirchhoff's loop type thing, here VR plus VL plus VC is going to equal to 0. So if I take and I plug these things in, what I have is L di dt plus I times R plus Q over C is equal to 0. Now we're going to do the same thing that we did before. We're going to note the fact that I is equal to dQ dt, just like that. And we're going to plug this in here. When we do that, you have L, two derivatives of charge with respect to time, plus R, one derivative of charge with respect to time, plus Q over C is equal to 0. Now, the approach to solving this is identical to the solving, you know, our equation right here, I believe. Here. What we did is we guessed a solution that looks something like this, and we're going to do the same thing here. Um, we're going to guess a solution uh, that looks something like Q equaling A times E to the plus or minus I bt. We're going to guess something like that. Okay? Now, to massage this into the form that I want, what I'm going to do is to divide both sides by L. That way, our leading derivative term here with two derivatives is a little cleaner. Now, you can see, hiding inside these terms right here, things that we've seen before. Like, for example, 1 over LC is omega squared, from this problem right here. And, from here, L over R is the time constant that we saw, way back when. So, these are things that have some familiarity to them. But we're not going to write them that way, and you'll see why. So the guess is, basically, or at least the process is to take your derivatives of q with respect to time, and then plug them in, and then, ask the question, what is b equal to? All right. So let's do one derivative of q with respect to time, and as I pointed out, what happens is you have plus or minus IB come down. Leaving that up there. You take another derivative of q with respect to time, and you get the plus or minuses kill each other off. The I hits the I and creates a negative sign. You get a b squared. Like that. Now, I'm going to pick a sign here. The general solution is to leave this as plus or minus. But just to make my life easy, what I'm going to do is I'm going to choose, I don't know, why don't I choose the minus? I want to do that. What the heck? I'll choose the plus. So, what that does is to make this look like I times b AE to the IB times T. This will be minus B squared AE to the IBT. Now, you can choose these because we're not looking for a general solution, we're looking for a specific solution. Okay. And if things don't work out, B will adjust itself. So now what we do is we plug these things into this. So it's dq, two derivatives of q with respect to time, that's your first term, minus b squared times AE to the IBT. The second term is a plus R over L times dq dt. dq dt is IB AE to the IBT. The last term is plus 1 over LC times Q, and Q is AE to the IBT, and that's equal to 0. So that goes because that's a like term across all, and what we have is minus b squared plus R over L times IB plus 1 over LC is equal to 0. And we need to find b. The first step I'm going to do to doing this is to just multiply through by a negative. B squared minus R over L times I times b minus 1 over LC is equal to 0. And then, it's our friend, the quadratic equation. And that's because, here we have something that looks like A b squared plus vb plus c is equal to 0. Okay? And we want to find b. So, here b is going to equal to minus big B plus or minus the square root of big B squared minus 4 times a times c divided by 2 times a. If I plug stuff in, noting the fact that a is equal to 1, b is equal to minus r over L times I, and c is equal to minus 1 over LC, then what I have is that b is equal to r over L times I plus or minus the square root of b squared. When I square this, it's r over L times I times the negative sign squared. The negatives are going to kill each other off, but the i's, when they're squared, give us a negative. Minus 4 times a times c. Divided by 2a. So b here is equal to, if I go ahead and multiply the two through, r over 2l times I plus or minus the square root of 1 over LC minus r over 2l squared. So that's our solution. Now, if I put that into my Q here, and we chose a form that looks like this. When I put this in, this is the same thing as e to the I times b (1 over LC minus r over 2l squared times t). Now what happens here is this I is going to move through this. I is going to hit I and make that a minus 1. And then you'll have an I that sits out in front of this. Now I'm going to call this right here omega prime. Okay? So let me just go ahead and carry that out. I times an I is a minus 1. Then what I'm going to do is to break up this addition here by putting another exponential there, because this is exponent math. This is the same thing as e to the I times this times e to the I plus or minus this. It's just, exponential math. So I have a plus or minus I omega prime t. Now what I'm going to do is to use the Euler equation on this. E to the plus or minus I omega prime t is the same thing as cosine of omega prime t plus or minus I times sine of omega prime t. And like I said, we don't care about the imaginary part. The imaginary part in this particular case It doesn't give us anything relevant. We want real stuff, stuff that happens in what you could, sort of think of as the real world. Okay. Now, but before I do that, what I'd like to point out is the argument here. I'm going to put it here so it's a little bit easier for us to stare it at in his face. Because look, L, C, and R are components that we choose to be within our circuit. Okay? So it is possible to choose components so that 1 over LC is bigger than R over 2L squared. In that case, what's up under the square root here is going to be a positive thing. And if it's a positive thing, then when you take the square root of it, it's a real number. So in the event that 1 over LC is greater than R over 2 times L squared, what happens is that this remains real. You can use the Euler equation on here to expand it, and this is going to oscillate back and forth. In this case, which I'll call case number 1, your solution for just your charge as a function of time would look something like A times e to the minus RT over 2L times cosine omega prime t. Oscillates back and forth with the cosine. This is a dying exponential. So what you would expect to happen would be over time, as this thing oscillates from positive charge to the negative charge, it's going to oscillate back and forth, and over time it's going to die off as the resistor eats up the energy that's required to keep it moving, because the resistor is going to convert that energy to heat. Now in a situation like this, we call this underdamping. Things that are underdamped are allowed to oscillate back and forth. They're allowed to get one off. But what about a situation when 1 over LC is less than R over 2L squared? Well, in that situation, this is a negative number under the square root, which means that you pull that out as an I, which means that your exponential here, omega is imaginary. I times an I makes it not imaginary anymore. It becomes negative. And what happens is this thing dies off. This plus or minus here, the correct choice for this is a plus, just like what we did before. So the negative times, or the I times an I makes this negative, and then what happens is that you have a very quick, drastic drop off. We call that overdamping. It isn't even allowed to oscillate once. It just goes like that, and that's it. Your charge is gone, as the resistor just eats it. The minute it passes through, it just eats up the energy that's moving it. Now there is a third option. The third option would be when 1 over LC is equal to R over 2L squared. In that case, omega prime is equal to 0. This is 0. And then you just have damping, and that's it. And it's not as, I guess, as overzealous as overdamping is. We call that critical damping. Now, what we're interested in this class are situations in which things are allowed to oscillate back and forth in the circuit. These are both valid, but it's the underdamping situation that's a little bit more interesting to us. So we're going to go with that solution. Okay, so let me take that solution there real quick. I'm going to go to another page over here and paste it. I also want to grab my omega. Right there. And like I said, the assumption that we're making is that this leading term, this 1 over LC, is greater than this, so that you're able to have this thing not over damp, but under damp. So this right here is our charge as a function of time. I would like to point out though, if you look over here, just like normal, when we start off, when we close our switch, our capacitor is fully charged. So if I look over here and I put in t is equal to 0, and note the fact that at the very beginning I should have maximum charge Q naught. T is equal to 0 and here makes this exponential equal to 1. T is equal to 0 makes this cosine equal to 1, which means that, as before, A is going to equal to Q naught. Okay, so my charge as a function of time is equal to Q naught times e to the minus RT over 2L cosine of omega prime times t. My current, my current I get by taking, a derivative of Q with respect to time. So when I do dq dt here, Q naught comes out. That's constant. And, I have a bit of a mess in here. I have to use not only the product rule, but also the chain rule. We'll start off with this term right here first. The derivative of this times this. That's going to bring down a minus r over 2L. Give us an e to the minus RT over 2L back. And then we just have our cosine of omega prime t. So that handles the product rule and the chain rule for just this first term. So it's the derivative of this times this plus the derivative of this times this. Well, the derivative of cosine is minus sine. When you use the chain rule, that's going to pull an omega prime out. So there's a minus omega prime e to the minus RT over 2L times sine of omega prime times t. So generally what we do is we just pull the minus sign out, and our current as a function of time is minus Q naught times R over 2L e to the minus RT over 2L cosine of omega prime times t minus, plus omega prime e to the minus RT over 2L sine of omega prime times t. Now, if you really wanted to, you could further simplify this and go ahead and pull out the decay part, which is this, since that's a like term. And then what you have in here is just the periodic behavior, just the stuff that oscillates, which would be R over 2L times cosine of omega prime times t plus omega prime sine omega prime times t. And there you go. So now you have your charge as a function of time and your current as a function of time. And as you can see, the addition of the resistor to take energy out causes this decay. Here the decay is oscillatory, big oscillations and smaller, 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 but it could just damp it very quickly or damp it, like I said, critical damping is when you're on that cusp where a little bit on one side you damp under and a little bit on the other side you damp critically, or not critically but over. So this is sort of an example of what the damping looks like. All right. So an overdamp thing is going to be damp straight down. A critical damping is going to look something like this. All right, let's go back to that. So this right here is an example of what this looks like, just from a damping standpoint. So what you're looking at right here, where it oscillates back and forth like this and gradually dies off, that right there is an example of underdamping. So critical damping would be when, if you look over here, where's it at? Further down? No, here it is right here. So, critical damping is when they're equal, when your omega term goes away. And then, over damping is going to be when things line up to really knock this thing out. Okay? So your decay here is much greater. So if you look over here, this right here would be an example of critical damping. And then right here where you're just taking it down really quick, this is an example of overdamping. Now, here's an example right here. We have an RLC circuit. You have a 10 ohm resistor. It's placed in series with an inductor and a capacitor. If the capacitor is charged to this before discharging, what I want to know is what the frequency of the damping is going to be. What type of damping are we looking at? And what's the period of oscillation, if any? Okay. And I also want to plot things. So let me go over here and still my circuit. So here's my circuit right here. And we'll start off just by writing out our givens, and I'm going to still my equations. So what we've been given here is the following. We have a resistance of 10 ohms. We have an inductance of 1.5 times 10 to the minus 4th henries. We have a capacitance of 3 times 10 to the minus 6 farads. We know the amount of charge our capacitor is initially charged to, which is 2.5 times 10 to the minus 4th coulombs. And what we want to find is the frequency of the damping, the type, the period of oscillation, and any plots. Okay? So let's go over here and grab our equations. Specifically, I'm going to grab these two right here to begin with. I'll put that here. And then let me grab my other one right here. For I. I don't think we really need it, but we'll grab it. I'll put that right here. Just like that. Okay. So why don't we start off with omega, because we're going to need that. And the behavior of omega is going to tell us whether or not we're dealing with a over, under, or critically damped thing. So omega prime is equal to the square root of 1 over LC. L is 1.5 times 10 to the minus 4th henries. C is 3 times 10 to the minus 6 farads. Now, then we're subtracting R over 2L squared. That's 10 ohms over 2 times 3, whoops, sorry. Hold on. That's henries, not coulombs. I don't know why I did that there. Let me fix that. Sorry about that. 1.5 times 10 to the minus 4th henries. Square that. Then let me accommodate myself here just a little bit. Just need a little bit of room there. And that's all square rooted like that. Okay, so let's see what R omega looks like. Okay, so it is the square root of 1 divided by 1.5 times 10 to the minus 4th times 3 times 10 to the minus 6 minus 10 divided by 2 times 1.5 times 10 to the minus 4th, and then I gotta square that, and then in my square root. Now, when I do this, I get 3.33 times 10 to the 4th radians per second. It's a positive number. So if I go over here and I look at the bottom with my damping types, underdamping, overdamping, critical damping, when this is greater than this, it's a positive number under this, which means that I'm dealing with a situation that's underdamped. So what type of damping is this? It's underdamping. So we have our angular frequency. Now let's find F frequency. So omega, remember, is 2 pi over the period, and 1 over the period is frequency. So my frequency here would be omega divided by 2 pi. So if I take this and divide it by 2 pi, I get 5305 hertz. So what this thing does is to oscillate back and forth 5,305 times a second. That's my frequency. What's the period? Period is 1 over the frequency. That is 1.88 times 10 to the minus 4th. So here's my period. Oops, I didn't want to do that. I don't want to do this. There you go. We have the frequency of the damping. We have the period of oscillation. Now let's plot our current and also our charge. There you go. So this right here is current as a function of time. This right here is charge. And what you can see here is that at the very beginning, where I'm charged up to 2.5 times 10 to the minus 4th coulombs, as charge moves from from the negative side to the positive side, what that does is drive current through the circuit just like that. Okay. Now there's a bit of a lag here if you take a look. That's a consequence of the self-inductance of the coil. But here it comes. And what you'll notice here is the current oscillates between positive and negative, and then very quickly sort of dies off. The charge oscillates from positive to negative, and then very quickly dies off. And that's because the resistor is taking energy out of the circuit as this thing oscillates back and forth. Now, so that's it. That's a brief rundown of the different types of circuits that you see. You have, RL, RC, LRC circuits, with the three big basic components. Pretty much any component beyond this is going to involve solid state stuff, which I've mentioned, which, if you were to take a more advanced class on electronics, you would go into great detail about. That requires a discussion about semiconductor theory and stuff like that, which we're not equipped to deal with. So that's That's it for this chapter, and I will see you in the next chapter, which is going to deal with light.